to run faster, or this improvement is achieved by program transformations that are traditionally known as the optimization. That is what algorithm you are developed. That algorithm, straightforward algorithm, may be made to run faster or takes place, and that is that transformations needed for making this algorithm optimized form, and that is known as the code optimization. Compiler that apply code improving transformation is known as the optimizing compiler. Basically, this phase is not mandatory for the compiler. All compiler does not support this, but which compiler supports the optimization techniques? This is basically, these compilers are known as the optimizing compiler. Now, optimizations are classified into two categories. One is the machine independent optimization, generic optimization, and another one is the machine dependent optimization. This is basically this most important criteria is the machine independent optimization. But that is, the optimization techniques do not depend on the architecture. Optimizations are classified into two categories. Machine independent optimization are the program transformations that improve the target code without taking into consideration any properties of the target machine. But the machine dependent optimization means this is based on the register allocation and utilization of special machine instruction sequence, and this fully depends on the machine architecture. Here actually code optimization basically will deal with the machine independent optimization. In the next chapter in the code generation, we will see little bit about the machine dependent optimization techniques. What are the criteria for the code improvement transformation? That is, the base program transformation are those that yield the most benefit for the least effort. This is number one. The transformation, that is the way you are optimizing the code, must preserve the meaning of the programs. That is, the optimization must not change the output produced by a program for a given input or cause an error like division by 0, which was not present in the original source program, like these things. That means the meaning of the program and actual output and actual logic should not be changed during the optimization. Next one. A transformation must, on the average, speed up the programs in terms of the speed of the execution, then there is no need for such type of optimization. This is the thing. And that is, the transformation also must be worth the effort. That is to benefit, you need to go on the cost benefit analysis of these things. What improvement you are getting after optimization, and what skills or what cost, that is what manpower or whatever may be things, you have to give or you have to effort. That is the thing. That is cost benefit analysis that is very much required. with some example, uh, you just see the need for the optimization. This is also basically what we have discussed. The same thing is written there. Just see, suppose need for the optimization, first one, basic idea. The programming language permits many flexibilities, often leading to inefficient code by the programmer. For example, A assigns to A plus 1. A is the real type. Optimization of the statement may modify the equivalent assigns to A plus 1.0, thus avoiding the runtime conversion. This is one aspect. Number two, this is one of the examples, or this is one of the criteria for the optimization need of the optimization. Next one, the optimization allows programmers to write code in a straightforward manner, expressing their intention clearly and allowing the compiler to make choices about the implementation details that lead to the efficient code. There are various approaches for the code optimization, but you can understand why we should go for the code optimization. That is what is the basic objective of the code optimization. Now, next one. What is the problems in optimizing compiler design? Basically, code optimization is not a just simple things. It's not an easy techniques. You will see the optimization technique may be easy one, but does not mean that when you are writing the optimization compiler and the difficulty you will get in generating the optimizer codes, that may be difficult one. That is, designing optimizing compiler is further complicated by the following issues. First one, usually an optimizing compiler takes the intermediate representation of the program code and replace it with a better version. And in the process, high-level redundancy in the source program, such as an inefficient algorithm, remains unchanged. This is a thing. That means program code modifying these things, it is not modifying the algorithm. It is not permissible. Modifying the code little bit so that it can run faster. It is not modifying because that will violate the property of the optimization. And modern third-party compiler usually have to support several objectives, for example, defined architecture, making it difficult more to optimize well for all the cases. This is the thing. That means when you are going for the machine-dependent optimization, it will be very difficult to cope with the various situations. You have to face various strategies. You have to face various obstacles regarding these things. This is the problems of the optimizing compiler. Number three is that a compiler typically deals with only a small part of applications at a time. At most, a module, usually a procedure, the result being, and it is unable to consider important contextual information. Again, I am repeating these things. That is, a compiler typically deals with a small part of an application at a time. These are things. And at most, a module, maximum one, or maybe a procedure. And the results being, it is unable to consider the important contextual information. These are things. If your code contains several modules and compiler while working at a module one time, this is basically, and mostly code optimization are basically the local optimization, that is module by module optimization. This may not affect actual effect, or this may not reflect the proper optimization if you go for the considering the entire program at a time. But compiler mostly not doing these things. That is, considering all the modules at a time or entire program at a time, it does not do these things. This may be another problem. Next one, we will see different classification of optimization. Different classification of the optimization, and this is the most important one. the most commonly used, and all are basically machine independent optimization techniques. And this is applicable to any of the programming language in any of the architecture. The commonly used optimization technique can be classified into various classes by considering the dimensions of the classifications. You just see, first one is what is the scope of the optimization. You need to consider the effect of a particular compiler optimization can be anywhere from a single statement to an entire program. And in this direction, optimization techniques can be classified as, first one is the p-fold optimization. This is usually performed late in the compilation process, and p-fold optimizations examine at most a few instructions to transforming them into other less expensive one. What is these things? You know, multiplication operation is much expensive compared to the addition operations. We can try, that means multiplication variable x into 2 can be the addition of x plus x. This may be done. That is, this is one of the examples of the p-fold optimization. And here we are reducing the cost of the operation. This can be done with the p-fold optimization. Next one is the local optimization. This optimization basically operates on a single basic block. The block by block or module by module optimization, what I have told you. And this is basically, most of the optimization are basically working in this way. Loop optimization. These optimizations acts on a number of basic blocks which make up a loop. And loop optimizations are the important because many programs spend a large percent of their time inside the loops. In loop, you can optimize, we will see, and this is one of the efficient optimization. You can reduce some time based on the loop optimization. Next one, global or intra-procedural optimization. This type of optimization acts on the complete control flow graph of a single procedures. And next one is this is not done frequently, global or inter-procedural optimization. And next one is the inter-procedural or the whole program optimization. This is also same thing. The most powerful of all, in some ways, that is considering all the modules, considering the entire programs you are going for, you are going to apply the entire optimization techniques. The most powerful of all, in some ways, they optimize interactions between the procedures. A simple example is to take a call to a function with constant parameters, copying the code of the functions and substituting the constant parameters throughout. This type of analysis is often very limited in order to deal with the complexity of an object as well as the whole program. That I told you, that means whole program optimization is not done physically. This is the concept, and usually mostly we are dealing with the local optimization techniques and the loop optimization techniques. And you just see some more strategies are there. That is language independent and the language dependent. This may be criteria. That is, most of the high level language share some common programming constructions and abstractions. That is decision, looping, encapsulations, and their similar optimization technique can be used across the language. That is, based on the feature, some optimization technique can be applied to some of the languages. This is the things. And machine dependent versus independent already are discussed. Now, next, we will see machine independent optimization. Basically, just see, can be local as well as the global. As I have told you, most of the optimization we are talking about the machine independent one. You just see, what is this? Local optimization, already I have told you, just comparison of the local and the global one. Local optimization are restricted to essentially sections of a program code, that is the basic block. In the for loop, you just for loop has been taken, There is a begin statement, curly bracket, and after doing something, you are ending these things. This is a local block, and you know that the scope of the variables lies, most of the scope of the variables, that is auto variables, are lies in this block. Basically, this is, and we are doing with these things optimization. We will try to optimize in this block, basically blocks. That is, its scope is limited. And basically, what is the advantage? Advantage of the basic blocks is that restrict the amount of the analysis required. However, it also restricts the kinds of optimization possible. For example, loop optimization sometimes cannot be performed locally. Why? Because if you apply the loop optimization locally in a block, that may affect in another loop, or that may affect in another portion of the program. That is the things. And the global optimization, it is applied on a larger section of a program, and typically loop or procedure or functions like these things. And you just see speed up factors up to 1.4 speed up can be achieved if you go for the local optimization, and you can achieve up to 2.7 factor, that is the things up to 2.7. This is due to the global optimization. But you just see both local and global optimization have their own importance because of the following factors. Local optimization simplifies the global optimizations. You just see elimination of the redundant computations from a basic block like these things. That is, you just see, suppose A star B, this expression has been repeated several times. If this expression has been used, that is F assigns to A star B, G assigns to F star B, M assigns to A star B, like these things. And what you can do, that is, you just have the value of A star B once and put it in a variable and use that variable or assign that value in other variables. This is the thing. That is, if A assigns to A star B followed by G assigns to A star B followed by M assigns to A star B. In that case, first computation is done and assigns to F, and then G assigns to F, and G assigns to F assigns to M, like these things. In this way, you can do. And local optimization can be merged with preparatory phase of the global optimization. That is, global optimization is nothing but it is the combination of the local optimization in an efficient way. This is the things. Now, next one, what are the factors influencing the optimization techniques? First one is the machine. Many of the choices about which operations can and should be done on the characteristics of the target machine. Sometimes it is possible to parameterize some of these machine dependent factors so that a single piece of compiler can be used to optimize defined machines just by altering the machine description parameters. That is, if the machines have similar type of architecture, in that case, optimizing a particular optimization compiler can work in the defined architectures. That is similar type of machine supports, three machines supports the similar type of architecture, and the same optimization compiler can be used to work on these things. Next one is the architecture of the target CPU. This is very much important. That is, first one is the number of the CPU registers, and basically in this way you can go for the optimization techniques. Local variables can be allocated to the registers and not on the stack, and this will improve your system performance. It will enhance the speed up of your program execution time, that is reduce your program execution time. That is the things. And risk versus CISC is also a factor for doing these things. And pipeline as well as the functional units. This is also important in dealing with the optimization phases. That means if you can break up your jobs into a number of sub jobs, and if you can go for your sub jobs parallelly, and you can apply the optimization techniques that affects this parallel implementation of your parallel execution of your statements, then this process, that is 5 clients as well as the number of functional units, have a major role to play in case of optimization techniques. Besides this, machine architecture, you can understand cache size and type. Cache size, more the cache, and where the cache is implemented, that is fully associated or KO associated. In that case, it will affect in your optimization also this thing. That means optimization technique, they will influence the optimizations. And the cache and the memory transfer rate. That is penalty for the cache misses or like these things, and this is mainly for the specialized applications. Now, themes or objective behind the optimization techniques. This is first one, avoid the redundancy. If something already computed like these things, as I told you, A star B, it is generally better to store it and reuse it later instead of recomputing it again and again. Optimization means less code, that is less work for the CPU, cache, and the memory. So it may be the faster. It should be faster. Straight line code, fewer jumps. This is the another motto of the optimization. Code locality, pieces of the code executed close together in time should be placed close together in memory. This increases the locality of reference. And next one, extract more information from the code. That is, more the information the compiler has, the better it can optimize. Now, are you understanding? So far I have discussed.
Yes, sir.
समझ में आ रहा है? Now, optimizing transformation, this is the basic techniques for optimizing, or optimization can be done based on these strategies. These are the compile time evaluation, common sub expression evaluation or common sub expression elimination, variable propagations, code movement optimization, strength reduction, dead code elimination, and most important one is the loop optimization. And this is basically machine, I should not say machine architecture independent one. Sometimes you can use this concept in that this is the concept you are going for the optimization, and that can be used for the machine dependent one as well as the machine independent one. But this is generic optimization techniques, and this is applicable to all the similar type of programming languages. First one, compile time evaluation. It deals with modifying the code such that the expression whose values can be pre-computed at the compilation time and used perhaps repeatedly in the execution of the program are identified. Then the computations of such expressions are moved to compile time rather than during the executions. And these are the two possible avenues that can be carried out, namely folding and constant propagation. Folding means corresponds to the evaluation of an expression with constant operation at the compilation time. As a result, fold expression can be replaced by a single value, hence the term is the folding. That is, F assigns to A star B, and later on you can use these techniques. That is, value of F in other expression. This is basically, that means reduce these things. This is known as the folding one. Suppose you just see here also area. Compute the area of a circle that needs the value of the constant pi, which is approximated by 22 by 7. The programmers often write the corresponding code as area equals to this one. And this compilation, that is 22 by 22.0 by 7.0, can be performed during the compilation to the machine accuracy used. And this is basically one of the examples of the folding. That is, typical application of the folding occurs in the address calculation for the array reference, where the products of many constants are folded into a single constant value. This is the thing. Now, actually, you know how array calculation, address calculation of the array has been done. Array, when you are defining the array base, this is the base address. You just define, that is first element of the array or the name of the array. Name of the array give you the base address of the array, or that A0 is basically same. Now, when you are calculating the array for the ith element, how you are getting, that is base address plus ai, you are dealing with the I into size of the each of the element, and you will get the specific address of A5 or A6 lines. In case of two-dimensional array, what you can do, you can convert your two-dimensional array into row measure or the column measure way in the one-dimension format, and then apply the same technique here. That means A plus your index value I into your size of the array elements, and in this way you can get any AI address. This is the thing. Next one is the constant propagation. Constant propagation, you just see, constant propagation corresponds to replacing a variable by a constant which is assigned to it earlier. So constant propagation alone does not lead to an optimization, but it may help in other optimization. You just see, constant propagation may help in folding the optimization. This is the piece of code. A assigns to 3.1 and X assigns to A into 3.1. So A into 2.5. Instead of doing these things, if you can write X assigns to 3.1 into 2.5, you may eliminate that variables A. A is not at all required here. That is, and if you can use the actual value of X, that is what you are getting, that is 3.1 into 2.5, you just see this type of computations is not at all required. And this is basically constant. You are propagating the value of the constants in everywhere, and basically you are folding this expression. That means minimizing the expression. Constant propagation, you just know, that is your constant propagation may be applicable where your A, that is wherever you are applying the value of A, that may be replaced with 3.1. But if your A is changed in somewhere else, then you cannot use the constant propagation techniques. This is the thing. You just see here. 9.1. Okay, I'm just telling you what is there in the 9.1. Yeah, you can see here. See this diagram. No, this is 9.2. Where is 9.1? Oh, this is. Isa, Isa, I have sent you a picture. forwarded to others. Have you forwarded these things?
Yes, sir.
You just try to explain the figure. Try to explain the figure. If you have understand, okay, just try to explain the figure as per the constant propagation terminology. You just see in the figure, you just see block number 9, x plus 17. Okay, the value of x you are getting from block number 6 and 7, mostly you are getting in the block number, that is value of x in the block number 8, you are getting equals to 5. That is, instead of x plus 17, you can write straightforward, that can be replaced by the 5 plus 17, that is 22. But you just see a plus 17, that is block 10, that cannot be replaced. Why that cannot be replaced? Why that cannot be replaced? কি বলছি বোঝা যাচ্ছে? Madhumoy, can you explain the figure? Explain. Do you have any problem? Do you have a microphone issue? I am telling, that is in this figure x plus 17, that is here folding can be done, constant propagation. X plus 17 can be substituted with the value 22 because x has the value 5. But a plus 17 in the block number 10, this is not possible. Why? A has also some values, but constant propagation is not possible here. Why? Anybody? You just see here in the block number 4, there is an assignment. A assigns to B. That is, B is getting the value of A. That means here you cannot change the value of A. Basically, A needs to be there. A needs to be, that means you cannot delete the existence of the A from here. This is the thing. But here, if we consider this is the end of the program, or there is things, that is after x plus 17, basically no variable is using the value of x, and that is why you can eliminate the value of x. This is the thing, and that you can substitute x plus 17 by 22. This is the things. Is it clear? Rahul, are you understanding?
Yes, sir.
Then why are you not responding? Nobody is responding. And what happens to the class? Last day also there are very few number of students. Today is also. Okay. Next one you just see common sub expression elimination. Just simple one. You just see here. A ascends to B plus C. X ascends to B plus C plus 5. This is a common sub expression. Then what you can do? Suppose temp ascends to B star C. Now X ascends to temp plus 5. Like this way, you can do these things. That is single computation. That computation is not at all required. But if you have these things, A ascends to B star C, then X ascends to B star C plus 5, in that case, computation is done in several times. And instead of doing these things, you just have the computation once. That is temp T ascends to B star C. And now you can use that B star C value anywhere as per the requirement. That computation only done in once. This is the things. Now you just see this diagram also. Common sub expression elimination. You just see here. You just based on the common sub expression elimination, you just try to explain these things also. Let's see. You just see A star B is a common sub expression here. Here A star B is a common sub expression. You just see A star B, but X plus Y is not a common sub expression. Why? Because you just see, although you are using X plus Y is used here as well as X plus Y is used here. That is block number 5 as well as the block number 8. But here you just see X plus Y, value of X can be maybe modified here. You just see X assigns to Z. That means value of X has been modified here. That is that value X plus Y and that value is not same. But here you just see A star B is not at all modified anywhere. You are using the value of A or B here, but it is not yet modified. That is the common sub expression. That is block 1 and block 10 has the common expression, that is A star B, but that is not same thing is applicable for X plus Y. Clear? And C star B, can I say C star B is a common sub expression? Olomirai, you just try to say, can we say sister B is a common sub-expression? Olomirai, are you there?
Yes, sir.
বলার চেষ্টা কর। You just see here, block number 1, block number 4, and block number 10. All are giving the same values. A star B, and from block number 2, what are you getting? C assigns to A, and now you are doing C star B. What is that? Same thing, that is C star B or A star B is the same value because C assigns to A. C and A have the same value. That is, you can eliminate the common sub-expression only once it will be used, and later on you can replace the common sub-expression with the help of the some values. This is the things. That is A star B, C star B, and A star B. That is 1, 4, and 10. All are the common sub-expression. Is it clear? But this is not the common approaches, because here you just say common sub-expression means basically we are dealing with the variables. Here A star B and A star B, same variables and same operator, but here the variables is different, and this is very difficult to for a compiler to understand that these three expressions are the common one. Okay, basically today I will not continue more. Tomorrow I will take the class at the same time, and tomorrow, and if required day after tomorrow also at the same time. Okay, that is, and Isa and Rahul, you just tell others, those who wants to join within 8:55. Must join within 8:55.
Okay, sir.
At least they should try to join at least 10 minutes before the class. Tomorrow I will continue this discussions, and class will be from 9 a.m. Okay.
Okay,
Okay,
sir.
sir.
Thank you, sir.